Hello, today we're going to talk about the mean value theorem for integrals. This is section 5.7. Remember we had the mean value theorem for functions in section 2.3. This mean value theorem said that if we had a continuous function defined on a closed interval, maybe something like this, then there's at least one number in this interval at which the slope of the tangent line is equal to the slope of the line that connects the two endpoints. Here's the f of b minus f of a divided by b minus a. There's the line through the two endpoints. That's the expression on the right-hand side. There's at least one number in here, maybe it's right around here maybe, at which the slope of the tangent line is the same as the slope of the line through the two endpoints. We needed our function to be continuous in here, had to be nice and smooth. We weren't really, this is where the derivative comes in. I need the derivative right here. Slope of the tangent line and then this was roughly the average slope. We have a mean value theorem for integrals that says this. It says, given a continuous function, I'll draw a positive one, kind of like what we had up there. We know that the integral from a to b can give us this area in here. That area right in there. So this is the area under the curve. The mean value theorem for integrals guarantees at least one number c in here at which the area of this box, height f of c and width b minus a. So let's see, let me just kind of guess a value here. And maybe this box right here has the same area as the blue shaded area, the area of the box with height of f of c and width b minus a gives us the same as the area under the curve. Kind of interesting, but it works. Let's see. Here I've given you f of x is equal to 4x cubed, so that's going to look something like this, kind of steep and through the origin. So let's get to where we can draw that. Let me draw it a little bit thicker. It's going to be steep, like that. And on the interval from 1 to 3, this box is in a certain amount of area. Let's find that area. From 1 to 3 of 4x cubed. It's an easy integral to do. You add 1 to the power, divide by the new power. We just get x to the 4th because the 4's will cancel. From 1 to 3. Then you put the 3 in there. 3 to the 4th minus 1 to the 4th. 3 to the 4th is 81. 1 to the 4th is 1. So 81 minus 1 gives us an actual area of 80 square units. So now there's a guarantee that there's some value for which f of c times b minus a is equal to the integral. So we're going to plug in c for x and we'll get 4c squared. 1 and 3 are our a and our b. So we're going to have 3 minus 1 here. And then we calculated this number over here to be 80. And now we're going to solve this equation for c. This is 2 times 4 gives me 8c squared is 80. So c squared is 10, and in that interval, c would have to be the positive. square root of 10. Square root of 10 is what? How big is the square root of 10? Let's see. Let me make sure I calculate all this right, because square root of 10 would be bigger than the square root of 9. Well, let's see. Oh, that should be c cubed. There's my problem. I knew that number was too big. This is cubed. Let's fix that. 4c cubed. And this is c cubed here. Here's where I need you guys in class to tell me where I make my mistakes. So c is going to be the cube root of 10. Now that makes more sense. That's a number that fits in here. And my guess is that it's somewhere over here. So let me put it in red. Cube root of 10. That it's this rectangle, maybe even closer to 3, that has the same area. Okay. All right, let's do the next one. We've got f of x is the sine of x between 0 and pi. So that's where the sine does one of its little here. There's the sine of x from 0 to pi. Let me make that prettier. Make it bigger. 0 to pi. My scale's still not right because pi is 3 and it looks not big enough to be where my 1 is, but my scale and my x and y axis are different. So what we want to do is find where f of c times b minus a is equal to the integral from a to b of f of x dx. So let's do it all in one swoop. F of c in this example would be the sine of c. B minus a is pi minus 0. And then over here we're integrating from 0 to pi sine of x dx. So this over here will simplify to pi times the sine of c. The integral of sine is minus cosine. Cosine of pi, and then minus a minus cosine of 0. Cosine of pi is -1, and cosine of 0 is +1. So I'm going to have 1 plus 1. That's an area of 2. So I've got pi times the sine of c is equal to 2, which says the sine of c is 2 divided by pi. And now solve for c. C is going to be the inverse sine of 2 divided by pi. So you didn't think it was going to be a nice integer value now, did you? It wasn't going to be. Okay, let's do one where we have to do a substitution integral. Let's write out the mean value theorem for integrals again. That f of c times b minus a is the integral from a to b f of x dx. So here f of c will look like c divided by 1 plus c squared. B minus a is 1 minus a -1. And then over here I've got to integrate from -1 to 1 x over 1 plus x squared. So on the left-hand side I'll have 2c on top and a 1 plus c squared here. Now, this is a substitution integral because the stuff downstairs is 1 degree more than the stuff upstairs. So we do that by taking u to be 1 plus x squared. Then remember we calculated du, which is the derivative times dx. Look up in here, the x times the dx is what we need to substitute out. So I take the 1/2 over with the du. And now the integral is going to look like this. We're going to have an integral. We won't worry about the numbers just yet. U's on the bottom, so let's write that as 1 over u, and then 1/2 du is x dx. So you have 2c over 1 plus c squared is equal to 1/2 times the natural log of u. We need to go back into our original variable. And that'll be a 1 plus x squared. Then, by gosh, we got to try to solve this for c. Oh my, that looks like it would be difficult. We might need to numerically solve this for c. This is quite the problem. Well, what I would do is maybe multiply both sides by, oops, I need to put the numbers in, sorry, this is what I forgot. I got to put those numbers in, so we'll have 2c over 1 plus c squared is equal to 1/2, this is going to be the natural log of 2, minus the natural log of 2, right? Because negative 1 squared. Oh, now this isn't so bad, because this is going to be 0 over there. So let's take it up here. We're solving 2c divided by 1 plus c squared is equal to 0. And so the only place that is 0 is where 2c is equal to 0. And that's where c is 0. By gosh, that is a nice integer value, and it's smack dab in the middle of that interval. The next application just comes from rearranging the expression from the mean value theorem for integrals. If we take the b minus a and divide both sides by it, that says that there's some value of the function that equals the area divided by the length of the interval. Well, you can think of the area is the total of all of the y values divided by the length of the interval. If you take your total and divide by how many you have, then you've got an average value. And that's what this is called, the average value of a function. So we're looking for the average value of a function, and we do that by finding the area under the curve and dividing by the length of the interval. So here are some examples for average value. Let's go back to our sine integral, and let's compute the average value of the sine of x. So the average value let's write down the formula. It's 1 over b minus a times the integral from a to b of f of x dx. So here we're going to have 1 over pi minus 0 times the integral from 0 to pi of the sine of x dx. That's the one that we did just a second ago, and we got that that integral was equal to 2. So this integral is 2. This is 1 over pi, and so we have that the average value is equal to 2 divided by pi. Okay, so let's do some substitution integrals. Find the average value of that one. So we're going to do the average value. Write down the formula again, help you remember it. 1 over b minus a times the integral from a to b f of x dx. So in our case, we have 1 over 4 minus 0, integral from 0 to 4, square root of 4 minus x dx. And the square root is a 1/2 power. So I have a quantity, that's the giveaway that we need to use substitution. So I'll go over here and say that we're going to take u to be 4 minus x, so that du is minus dx. I don't have a minus over here, so we'll move it over there with the du. And when we make our substitution, our integral, we'll pull the minus sign out here. This will be u to the 1/2 times du. When you integrate u to the 1/2, you add 1 to the power, that gives you u to the 3/2 times 2/3. When I simplify that, 2 goes into 4 twice, so that gives me a negative 1/6 u to the 3/2, and u is 4 minus x. And then we evaluate that from 0 to 4. Let me factor out the 1/6. When I put the 4 in there, I get 0. When I put the 0 in there, I get 4 to the 3/2. 4 to the 3/2 is the square root of 4. That's 2. 2 cubed is 8. I've got a -8 there, but a negative outside. So let's multiply the two negatives to get a positive. Positive 8/6, which is 4/3. On the average, that's a value of 4/3 in there. All right, sounds like we can do another one. We've got this parabola that opens upward on the interval from -1 to 1, and we want to find the average value. So you got the formula looking up there. Let me just fill it in. 1 over b minus a times the integral from a to b of 2x plus 3 squared. Now you can square this, multiply this polynomial out and then integrate term by term. But where's the fun in that? Let's do our u to u substitution. U is the stuff inside. Du is the derivative times dx. Okay, since we don't have a 2 here, we just solve this for dx. And now make the term by term substitution in here. So we get our average value is 1 over 2, then the integral of u squared times 1/2, another 1/2 out here, times du. So we have 1/4, integrate u squared and get u cubed over 3. Let's put that together as a 1/12. U is 2x plus 3 cubed. So that's over 3, got that. Now from -1 to 1. The 1 goes in first. Let's factor out the 1/12. 1 times 2 is 2, plus 3 is 5, so I have 5 cubed. 1 times 2, -1 times 2 is -2, plus 3 is 1, so minus 1 cubed. 5 cubed is 125, minus 1 is 124. So we have 124 over 12. Looks like both of those are divisible by 4. How about 31 over 3? Okay. Nice little application of a definite integral. And now I've got a word problem here where we can find an average value to mean something to us. Records indicate that t hours past midnight, the temperature at the local airport was given by this function, -0.1 t squared plus t plus 50. Right? So if t is hours past midnight, then t is equal to 0 corresponds to midnight, which says at midnight that was 50 degrees Fahrenheit. We want to find the average temperature at the airport between 9 a.m. and noon. So 9 a.m. is going to be 9 hours past midnight, right? And noon is going to be 12 hours past midnight. So our interval is from 9 to 12. So we want average temperature. Okay, so there's temperature. Average temperature is going to be 1 over b minus a times the integral from a to b of -0.1 t squared plus t plus 50 dt. That's a 1/3. This is just a term-by-term integration. So this is going to be, well, I'm integrating. Let's get rid of the integral sign. A -0.1 t cubed over 3 plus t squared over 2 plus 50t from 9 to 12. So we've got 1/3 here. That's 1/10, so let's make that -1 over 30. 12 cubed plus 12 squared over 2 plus 50 times 12. Now we put the 9 in there. -1 over 30 times 9 cubed plus 9 squared over 2 plus 50 times 9. tell you what, those don't look anything like numbers I want to compute. I can't do 12 cubed. I can't do 9 cubed. I'm just going to punt from here. So we're going to say it's a certain number of degrees Fahrenheit. How about that for a wimpy ending? And that's it. That's what we've got in this section. The mean value theorem for integrals says that there's some rectangle whose area is the same as the area under the curve. Not just some rectangle. It has to be a rectangle where the height is a value f of c, where c is between a and b. And then the average value is just the total area divided by the length of the interval. 1 over b minus a times the total area.